In the last video of our series, we're going to be looking at how to use the GPU for training and deploying neural networks. So GPUs are very commonly used for training neural networks because of the parallelization that you get compared to using CPU. So you can pass much more data through your neural network much quicker, and this just speeds up training of your models. So we need a specific version of MXNet to be using GPU. We need the CUDA versions, so you need to have a NVIDIA GPU, you need to have CUDA installed, and then you need to install the CUDA version of MXNet. So when you're pip installing, you would typically pip install MXNet, and to get the CUDA versions, you pip install MXNet-CU, and then the version of CUDA. So if you're on CUDA 9, it would be 9.0 or 9.1. And the install instructions are available on the MXNet homepage, and so you can work through those to get GPU installed. Or if you're on SageMaker and you spin up a GPU instance, you'll have all the CUDA drivers installed for you. Much simpler way to get set up, or use the DL armies available on AWS. And so with all that set up, we can go ahead and import our MXNet libraries. So it's the same libraries as we used in the previous couple of videos. We've got Gluon, AutoGrad, and the datasets and transforms as well. So for our first use of the GPU, we're just going to create a really simple ND array of ones, but instead of allocating this on the CPU, as we've done previously, we're actually going to allocate this array on the GPU. And the way we do that is we specify the context for the array. And context is provided through an extra argument called CTX, and that's on the ND array that we're going to create. And we then pass the context of the device that we want this array initialized on. So by default, this would have been set to CPU, and so it would have gone to CPU memory. But here, by specifying GPU, we're going to put that on the GPU. And we can actually specify which GPU to use if we've got multiple GPUs. Here, we're just using GPU, but we could have specified GPU 0 to indicate the first GPU. Now that we've created X, which is 3 rows, 4 columns of ones, when we print out X, we can see where the context is. So it just shows here after printing, we've got an ND array 3 by 4 at the GPU 0. So it's actually being allocated to the first GPU. If we were to use the CPU as the context, when we were doing the operations on the array, we would actually use all the cores, as many as possible. But when we're dealing with GPUs, we'll only use the GPU that's specified for the context to do the operations. So here we'll just do we'll do the operations on the first GPU. And we have fine control over where we send the arrays as well. So we can move and transfer them from device to device. We can copy from CPU to GPU, we can copy GPU back to CPU, and we can do it between the GPUs as well. So here we've initialized on the first GPU, but we show an example of how to actually transfer that to the second GPU. This line of code will actually only work if you've got multiple GPUs. You'll get an error otherwise. But in this case, we're using a P3 8x large instance. So we've got multiple GPUs available. And we then take our array X and we copy to GPU 1. And if we were to print that out, we can see now we've got the ND array on GPU 1 instead of GPU 0. So it's the second GPU. We've got some implicit copying for some operations. So when we do a print, it actually brings it from GPU to CPU. And we've got as NumPy and as scalar, they're also going to do the same thing. They're going to bring it to main memory and CPU. And now, once we've got the arrays on GPU, we're obviously going to want to perform different operations. Almost all operators in the ND array module can be applied on CPU and GPU. But the one prerequisite for applying operations on the GPU is that the inputs to that operation have to be on the GPU already. And here we're initializing the ND array with uniform, same shape as before, and we're putting it on the GPU and GPU 0. Here, if we were to add the two arrays, so the array we've just created and the array from before, and you'll notice that the copy here is not in place. So we still have X on GPU 0. So we've got both of these arrays on GPU 0, which means we can add them together. And so this addition operation is going to happen on GPU 0. And the output will then be on GPU 0 as well. And so that was really a simple example. In reality, we want to be doing this for training neural networks. So we'll create the same neural network as before. And in video 4, we train this on CPU. And we saved some parameters to a file. And when we load in the parameters in our last video, we can specify the context that we want the weights of this model to where we want them to be loaded. And the default before was to load them into CPU memory, but now if we specify the context as GPU 0, we're going to be loading these parameters into the first GPU. And now the model and the operations that are being performed on the model are going to happen on the first GPU instead of CPU. So we'll create our input, just an example input. Our model is working on grayscale images of 28 by 28. We're working with the fashion MNIST dataset. And instead of loading in the fashion MNIST dataset here, we're coming up with a random array of values, and we're going to put them on the first GPU as well, which means because we've got the input on the first GPU, and all the weights of the network on the first GPU, which means the operations will now happen on the first GPU. So we can call net with that input, and the output is again assigned to the first GPU. This is all happening now on GPU as opposed to before it would be CPU, and we're going to get better performance because of it. And to work through a more comprehensive example of how we do the training across multiple GPUs, here we're going to be using the fashion MNIST dataset again. This is all stuff that we saw from the 4th video. We define a batch size, we've got our data sets and our data loaders, and we're going to apply the transformation steps. This is still all going to be happening on CPU. We're going to be loading into CPU memory, but then we're going to actually transfer the data, as we'll see later on, to GPU, and the operations of the network will be applied on GPU. For our multi-GPU training, we're going to first specify which devices we want to use. So in this example, we're going to be using 2 GPUs, and we have a list of devices. We've got GPU 0 and GPU 1. We're using the same network as before, and earlier on we loaded in some parameters from a file, and that was trained in video 4. Instead, right now we want to reset the parameters. So we're going to collect all the parameters and we're going to reinitialize them. So we call initialize. We're going to force the reinitialization because they've already been initialized from the file previously. And it's just going to make sure we overwrite them with random values. And then we specify the context. So previously, when we loaded from file, we specified that we wanted the weights to be put on the first GPU. Now we're doing multi-GPU training. We provide a list of devices that we specified, so we've got 2 GPUs. And now what this is going to do is it's going to initialize the model on both GPUs. So we're going to have the weights on each of the GPUs, which will mean we can apply and use the network on both GPUs on different parts of the data. We'll see how we do that later. As before, we set up a loss function, and we have a trainer, which is going to manage the parameters, updates, and specify the optimizer that we're going to use. So on to the training loop. We loop through our dataset 10 times as before. We've got 10 epochs. And within each epoch, we want to work through all the batches of our training data first. So we've got the loop here, which is going through the training data, and that's the data loader. We get data, which is the batch of images and the corresponding labels. And the data loader will load into CPU memory. So if we looked at the context of where data and label were, they'd be on CPU at this stage. And our network, we want to apply on the GPU. So we need to move the data and send the data to the GPUs first. And because we want to use more than one GPU, we want to send some data to the first GPU and the other part of the data to the second GPU. And there's a really good function in Gluon that helps us do this splitting and loading. And so it's gluon, utils, and split and load. And what we provide to this is the batch or data, which is just could be an array, and then the list of devices. And this will then split the batch, in this case in two, and send the first half of the batch to the first device and the second half to the second device. Well, we want to do the same thing with the label as well. And we want to send the same part, the same corresponding labels to the same GPUs. And we get that by doing the same operation on the data list and the labels. I often call these different partitions of the data, and we will then see how we loop through the partitions and apply the network to each partition on each GPU. So for our forward pass, we want to make sure that we're in the auto grad record scope. So we're ready with the backward pass and we can work out the gradients. Within the auto grad record scope, we iterate through all the partitions as before. So we zip together the data list and the label list to make sure we have the corresponding labels for the data. And now we have a single partition, and we're looping through the partitions at this point. For every partition, we want to apply the network and then work out the loss. So the network is going to be applied on the same GPU as where the partition has been sent. In this case, we've got two partitions. So the first partition is going to happen on device 1, and that's going to be processed the first iteration of this loop. And then the second half, or the second partition, will be applied on a different GPU. And so then this can happen in parallel. And once both losses have been computed, we will then loop through the two losses, one loss from the first GPU and then the loss from the second GPU, and apply the backwards step on each loss. Now we've got a cumulative loss and the cumulative gradients. We can then apply the trainer step to all the parameters, and the trainer keeps track of all the parameters and which GPUs they're going to be on. They're going to be on both GPUs at this point, and we'll manage the updates of that. And we give it the batch size to do the normalization. The last step is we're just updating the training loss so we can get a measure as we go through each iteration. And this will run much quicker than with the CPU. You'll see we're down to 2 seconds per iteration as opposed to about 15 seconds with the CPU. And so that concludes our video series on Gluon. I hope you enjoyed it and learned a lot. Check out the website for more information, and there's some good tutorials there to continue learning.